Okay, next topic. This is in chapter 3. There's a section of pages, 8 or 10 pages about finding a parameter in a limit of integration. So in this case, suppose we have, we're going to compare these two definite integrals. In the first definite integral, you have to compute the exact area from x squared to the x-axis from 0 to 2. So it's this region. Every definite integral has a picture that goes with it. And you start by getting the doing the indefinite integral, you get the antiderivative, evaluate at the upper limit minus the lower limit. You get 8/3, which is 2 2/3, so 2.66. And that's what this exact area is. Which is, again, about 2.66, or exactly if you add the repeating. Okay, that's what we had done, so that's all review. But what's new this time is this problem on the second problem here. What if we have a parameter, not a number, 0, 2, not a number here, we now have a parameter b, a, t, p, some parameter in the limit of integration. So that's a whole class of problems, a parameter in your limits of integration. In this case, we want to find the b that makes this a true statement. This is an equation. It's an equation that involves an integral, but we know how to actually do things with the left-hand side of this. So maybe we can simplify the left-hand side here and get an equation that involves b. There'll be one equation, one unknown. Hopefully we can solve it and figure out what value b makes this a true statement. But let's, before we even do any of that calculating and the algebra, let's think about this pictorially. What does this look like? Well, I have a function x squared, parabola opening up, starting at the origin. And I want to go from 0, x equals 0 is right here, up to b. I want to know how far should I make b so that the area of this shaded region is exactly 9. I want the exact area of the shaded region to be exactly 9. So we need to find b, the wall that makes this happen. Where do I stop, right? We know if we stopped at 2, that's too short. The area is 2.66, we need it to be bigger. Should I go up to 3, 4, 5, 2.7? What is the precise value to put that ending wall, that right side wall, that will make the area exactly 9? There's some neat application problems in this chapter, but also your challenge problems that show you why you want to be able to solve problems that have a parameter in the limits of integration. So we're going to start with this one, and then we'll easily see that solving this equation could be messy, so we'll need some tech tools sometimes. Okay, so what we're going to do is simplify this. So if this was the example, which is find b that solves this equation here. So that's the problem we want to solve. Let's work to simplify the left-hand side of this. Just don't even think about the 9 for now. If I was going to do this, I first need to treat it as an indefinite integral, get the antiderivative, which is upper power over the power, evaluate it at the limits of integration, always the upper limit. So I plug in b for x, and I get b cubed over 3, minus the lower limit is 0 over 3, which is just 0. So I get b cubed represents the left-hand side, and that has to be 9. So now I'm looking at this equation. This is one equation, one unknown. It's a nonlinear equation because it's an equation in b, and b is cubed, right? So it makes it a cubic or a nonlinear equation. And I want to solve this. Well, these are things from the pretest. You can work to isolate b, but right now b is divided by 3, so I want to undo the 3. Multiply by 3, the inverse operation, division is multiplication. Whatever I do to one side, I do the other. So b cubed is equal to 27. Right now, I want to isolate b, but b is stuck inside a cube. How do you undo a cube? You apply the inverse operation, which is the cube root. Whatever you do to one side, you have to do the other. So I'm going to take the cube root of both sides of this equation. The left-hand side is just b. That's what I wanted by design. I wanted to isolate b. The right-hand side is 3. So we have found a value for b that solves this equation. Now we can say b is actually 3. That gives us an exact area of 9. You can check your work by computing the integral from 0 to 3 of x squared dx. You'll check your work and see that it is in fact 9. Okay, so we had a parameter in the limit of integration. It happened to be the upper limit of integration, but you could have one in the lower limit of integration as well. You might even have it in both limits of integration, but they have to give you a little more information to be able to find both a and b. When there's just one parameter in one of the limits of integration, you will get one equation, one unknown. That's something you can solve by hand sometimes when it's particularly easy like this one, and then sometimes you'll need a tech tool. So I'm going to erase the board and we'll put a few more examples up. Okay, suppose we want to do this problem. Find the value of a that solves this equation. The equation on the left-hand side involves an integral, a definite integral, but it has a parameter in the limits of integration. This parameter is a lower limit of integration, but very similar steps to what we just did. This time we'll be solving for a. We'll have one equation, one unknown, but it's likely going to be a much more difficult problem to solve. So let's see where we go with this. Let's, though, before we get to the calculus and the arithmetic, let's see what this function looks like. It's the cubic function flipped and then shifted up 4. So okay, so here it is in Desmos, 4 minus x cubed. That's our function in red. We want to go from some value a up to 1. So here's 1 right there. We want to go figure out how far to the left, where do I start over here? And then I'll stop right here at the wall. Maybe I'll add another function here, x equals 1. That green wall is the wall we're going to stop at, and we need to know what is the value over here, x equals a, that we start at, so that the area from the red, left wall to right wall, is exactly 4. And it's a good idea, again, to kind of maybe take a guess. If we went from 0 to 1, we'll have something less than 4, right? Because that rectangle right there would be exactly 4. So we probably need a little bit, a is probably going to be negative to get a little bit more. So let's see what happens when we solve this with the calculus now. Okay, so the left-hand side, ignore the 4 for a moment. Let's just treat this part in the box. It is a definite integral. First, we treat it as an indefinite integral. We get some antiderivatives. Evaluate those antiderivatives at the limits of integration. Always do the upper limit first. So 4 minus 1/4 is what? 15/4. So when I plug in 1 for x, the upper limit gives me 15/4 minus what happens at the lower limit. When I plug in a for x, I'll get 4a minus a to the 4th over 4. And now I have completed the integration for the what's on the left-hand side. Turns out to be what's in the box here. But I want to set that to be exactly 4. I want to find the a that makes this statement true. That must be exactly 4. So at this point, I want to find the a that solves this equation that's in the box. Okay, so there's some things I can do to simplify it first, but we're probably going to see that this is a quartic equation that there's no formula that we can use that we know to solve it. They do exist. And so we'll use a tech tool. But let's get a little further along then. So let's see, I have a 15/4. Well, let me just go ahead. The minus 1/4 a to the 4th, that's the highest power. We just write that first. Minus 4 times a. Bring this 4 to the other side, becomes a minus 4, which is minus 16/4. So 15/4 minus 16/4 is minus 1/4. That all equals 0. Let's see what happens. Could I factor? I could maybe clean it up a little bit. I don't know if it's going to help, but I could take out the 1/4 minus a to the 4th minus 16 a minus 1. Again, I'm looking at what's in parentheses to see, is it possible to factor that? No, we'll have a squareds Yeah, so we can't factor that using our basic foils. So we're gonna have to resort to a tech tool. There are ways to solve this using numerical methods. It's a class you take maybe in your junior year if you were a math major, but most of you aren't. So we're gonna just use a tech tool. We don't have to learn the numerical methods. Those are already programmed by tech tools. And so we want to solve this equation, either one, it doesn't matter. We'll put this one in red. We will ask Wolfram Alpha to solve this equation for A. One fourth is 0.25, so minus 0.25, A up to the fourth, minus 4 times A, minus 0.25 equals 0 for A. So we're just entering it in natural language processing. That's what's nice about Wolfram. Check that it did interpret what you wanted. You entered things correctly. Minus a quarter, A to the fourth, minus 4A, minus a quarter equals 0. Solve that thing for A. And it gives lots of different answers. We don't in this class, and again, unless you were a math major, you wouldn't do these ones that have these i's. Those stand for imaginary numbers. So we're going to focus on these two, the first two. A is negative 2.4987, negative 0.0625. You can ask for more digits. You can ask for exact forms, and it'll just keep spitting out longer, more and more precise values. Again, using a numerical method, that's beyond the scope of this class. But it is helpful to set up and solve and model these problems with the help of a tech tool. You can do some really neat challenge problems. Okay, so let me write these two values down and then we'll come back. Stop sharing the screen. So A is approximately minus 2.49. Let's just carry maybe one more digit, 9. And A is approximately minus 0.06263. Okay. Okay, so the tech tools solved this equation that said these values of A are the real values that will work. How would you check? You take A equals minus 2.499, plug it in for A here and there, check that it does equal 0, and it will. It's a tech tool. You do the same thing with the other one, minus 0.063. But let's go back to figuring out which one of these works, or do both of them work? And let's look at, go back to Desmos then, and see which one's going to make sense for us. Because when we asked Wolfram to solve this, it didn't know that there was a picture and there was a context for a problem and a particular model that we were actually working with. We know that, so we designed it that way. Okay, so let's put in x equals minus 0.063. Okay, that is the purple line now. The purple line goes, if we go from the purple line to the green line, from the red line to the x-axis, that area is exactly 4. And that's kind of what we guessed. We knew 0 to 1 wasn't going to do it. We'd have to go a little bit in the negative direction. So it does check our guesswork. Negative 2.59. Let's see about that. Oops. Now this other one I don't understand. Right, that seems like way bigger than 4. So that's a root that we don't need. It doesn't make sense in the context of our problem. So we've narrowed it down that this is the only one that makes sense for us. We found the value of A that solves this problem. We had to use a tech tool, so we had a parameter in the limits of integration. That parameter can occur at the lower limit or the upper limit. That creates one equation, one unknown. So you use your anti-differentiation to get it down to one equation, one unknown. Sometimes that equation is simple. You can use the techniques that you've learned thus far in your math career to solve that. Sometimes that equation is hard. You can't factor it, you can't FOIL it, but you can use a tech tool. a really nice tech tool that accepts natural language processing as Wolfram Alpha. We used that, and then we verified visually that this answer made sense with a picture of what this equation means for us. Okay, that's it for this lesson.